Good evening, Good evening, ladies and gentlemen, and welcome to the Recreational Astronomy Night for December 2024. My name is Tom Luton. I'm going to be your host this evening. Our usual host, Paul Markov, is unavailable. This evening we've got a short program because our annual meeting of the Toronto Centre of the Royal Astronomical Society of Canada is immediately following our meeting. Tonight we've only got two presentations. Claudio Oriani will be talking about the sky this month, and Arushi Nath will be talking about using N-body simulations to analyze transit timing variations in multiplanetary exosystems. Let's get the ball rolling with the sky this month and Claudio Oriani.
Thank you, Tom, for having me tonight, and good evening, everyone. That's Claudio Oriani from Richmond Hill. Tonight I will talk about the sky on the month of December. Note that during my presentation, all times are expressed in Eastern Standard Time, and unless otherwise noted. There's so much going on this month, so without further ado, let's start. At glimpse, we have Jupiter at opposition on Saturday, September 7th, so it's coming now. We have 3 meteor showers, so the Gemini, and also the Quadrantid, and also the Ursus. There are lots of going on. We have the winter solstice. The Mars is going to be very close south of the Moon. Unfortunately, there is no occultation this month, but good news, there will be an occultation next month. I will tell you later. And also Antares will be very close of the Moon at the end of the month. And we will reach perihelion on Saturday, January the 4th. Not much to say about the sunrise sunset. As you can see, today the sunrise was at 7:34 a.m., while the sunset was at 4:40 p.m. So we basically had 9 hours, 6 minutes of daylight. While on January 8th, we have just 2 minutes more of the daylight. So it's really changes so much. What happens is that it's pretty much the same. So what does it mean? It means that the astronomical twilight end today at the 6:23, when we have, as you can see, 11 hours and 29 minutes of imaging time, while on January 8th, we have 11 hours, 26 minutes. So we have a bunch of time to take imaging. The sky. So basically tonight at 9 p.m. you can see Cassiopeia, Andromeda, Perseus, and Pegasus. The fall constellation are overhead. So take advantage if you have the clear sky to take images to look at this constellation. While Taurus, Gemini, and Auriga are also well positioned high in the sky. Around 11 p.m. Orion, Canis Major, the Sirius, Monoceros, the unicorn, will get higher in the sky, not too high at our latitudes. One thing you can notice for this month, the winter hexagon, that basically is the largest circular pattern made of some of the brightest stars. It's not a constellation. And we have Rigel, here in Orion. And then we have Aldebaran in Taurus on the top here. We have Capella in Auriga. And we have the twins, Castor and Pollux. Pollux in Gemini and Procyon in Canis Major. So you can see a circle. The brightest star around, they are getting high in the sky. Today, if you look at southeast to southwest horizon, you can see Saturn in Aquarius, and this other circle is Neptune. Is also in Aquarius, almost 38 degrees above the horizon, while Saturn is 26 degrees. Still not too high, but you can have a look and you will notice that is like one magnitude is not blinking, so it's a planet. For Neptune is not visible to the naked eye. Going to the northeast, to the southeastern sky, you can see Jupiter, and you can't make any mistake because it's the brightest object to the eastern side. And you can also see Uranus on the top of Jupiter. You see all the winter constellations, so the Gemini, Auriga, and also the Taurus here, Orion to the east. Northwest, you can see that Big Dipper is reaching the lowest altitude for this year, while Cepheus is overhead. And the Lyra constellation with the bright star Vega is low to the northwestern horizon. Looking at the southwestern to the northwest horizon, you can see, as I said before, Pegasus, Andromeda, and Cassiopeia also overhead. Here, and Cygnus is the most prominent constellation on the western sky. Overhead, you can see again, you can see Andromeda and the double clustering Perseus, a lot of beautiful deep sky objects here. Let's go to the solar system. Let's start with the sun. So in August 2024, the sun reached its maximum activity for this solar cycle, but it's still very active. You can look at some websites I mentioned here, spaceweather.com and also the NOAA.gov. Also, if you can install an app on your smartphone, there is My Aurora Forecast, just in case to have a look if there is any coronal mass ejection and maybe possibly a northern light. That's the sun. I took this image a few days ago. It was on November 9 with a monochrome camera. You can see lots of things going on here. I inverted the colors because I wanted to emphasize the prominences and the beautiful filaments, some big sunspots. Probably you can see the sunspot better with the next image here. This is the normal colors. You can see the sunspots here on the limb, here, here, and here. Of course, this was a special hydrogen alpha telescope with a certified filter. The moon will reach its minimum distance to the Earth on December 12 for this duration, and is only 365,000 kilometers, while the apogee will be on December 24 before Christmas. These are the phases of the moon for the next few weeks. So the first quarter will be reached on Sunday, December 8th, when the moon will set around midnight. The full moon will be on December 15, and this December full moon is called cold moon. I don't need to explain why. The last quarter will be reached on December 22nd, while the new moon will be the end of December. So good imaging time by the end of this month. Of course, the moon is not showing exactly always the same part. We can see a little bit more because there is a libration. It's just the combination of the tidal forces from the Earth and the Sun. And this is what the moon is doing. So we can see probably 59% of the moon during a cycle. So we can see a little bit more the western side of the moon on December 5th, so tomorrow. Yesterday, there was something more happening on the northern part of the moon. And you can see the eastern side of the moon, we can see more than usual on December 18. And the southern part will be on December 16. This image was taken from nthsky.org. This is the website. There are a bunch of opportunities to see the moon and the planets and bright stars be very, very close together. The red rectangle is just a projection of a DSLR camera and 135 millimeters. So you can have a look and see what you can imagine in the next few weeks. Let's start with Moon and Saturn on December the 7th. So they're a very beautiful vision here. You can see they're in the same field of view. While on the next day, the moon will reach Neptune. If you know, take an image of the moon around this time that's mentioned here, you can at 11 p.m., you know that here there is Neptune. The moon will also be close to Uranus, not in the same field of view, and the Pleiades on December the 12th. That's a good view too. While this is happening the next day, December 13, from our latitudes, the moon and the Pleiades will be very close. The next day, the moon will meet Jupiter. And on December 18, as I mentioned before, look what happened here. So first, if you see midnight, the moon and Mars are very close. A few minutes later, moon, Mars, and the beehive in Cancer will be very close. There is no occultation from our latitudes, but as I said before, spoiler alert, on January 13, there will be a beautiful occultation of Mars visible from the North America a few hours after Mars will reach its closest approach with the Earth. So sign the date, save the date. On the 20th, the moon will be very close to Regulus in Lion, Leo, 1 a.m. It will also reach Spica in Virgo on the 24th. And this is also another beautiful view of the moon, very, very little sliver moon and Antares. They're very close on December 28th, around 6:45 a.m. before sunrise. And on January 3rd next year, moon will be very close to Venus. And again, we'll meet Saturn. Now, I mentioned the planets, but let's see something more about the planets. So this is taken from the journal. And so Mercury basically will be visible in the last few days of the month, will be visible before sunrise, while Venus is the most prominent object in the western sky after sunset, is an evening object, and same for all the other planets, including Neptune. This is also the brightness, and this is the diameter. You can see Jupiter is very big. Now, this is Mercury. The first half of December will be too close to the sun for safe viewing, but it will rise very early in the morning in the eastern sky and will be visible north of Antares starting on the 22nd. Will reach its greatest western elongation, best time of the year, the last opportunity to see Mercury before sunrise on December 25th. Venus is very bright in the evening twilight and finally climbed in the ecliptic in the western sky. So what happened the last few months, the ecliptic was very shallow. Now the ecliptic is getting higher and the separation from the sun will be higher and higher. You can see the shape of Venus. This image was taken from Millennium Square last year. Mars is getting closer and closer and closer. There will be opposition in January, and its magnitude will increase to -1 on December, -1, December 21st. Is well placed for the evening viewing. You can't make a mistake. It's a red object that is moving faster. Interesting about Mars, it will start moving in an awkward way. So the retrograde motion, I did some research here, and basically you can imagine to have a racetrack with two lanes. The inner lane is our orbit, the Earth, while the outer lane is Mars. What happens is that when both Mars and Earth are moving on the same direction, counterclockwise, the Earth, our planet, is moving faster because it's closer to the sun, inner lane. Initially, you see Mars moving forward in the sky, the prograde motion. As Earth catches up to Mars, from our perspective, we see Mars like slowing down, and then when we pass Mars, Mars is going backwards, retrograde motion. Obviously, this is an illusion, it's not real. It's the relative position and speed of the Mars and Earth. and then we'll start working again as usual. So basically, what happened if you see the numbers 1, 2, 3, 4, 5, the blue dot is the Earth, while the red dot is Mars. What happened on projection of the sky? You can see Mars going backwards, starting from here when we reach and go ahead, and then going back to this direction. This is from Wikipedia. Thank you. And then the star, although it's not the star of the month, is Jupiter because it's well placed and, of course, will reach opposition next Saturday when it will be only 34 light minutes away. Interesting things happening on Jupiter. On December 23rd, there will double shadow transit, Ganymede and Io. Is 3:25 in the morning. You can see both the shadows here. This is Ganymede and this is Io. And it happens again on the 3rd. You can see both the moons of Jupiter on the planet itself. It is 4 o'clock in the morning. If you want to see more about Jupiter, there are pages 226, 232 of the Observer Handbook. And you can also go on this website to see where's the great red spot, where the moons of Jupiter, and so on. Saturn is rises early in the afternoon in Aquarius, and the ring plane is exposed at 3.3 degrees tilt. Is getting shallow and shallow, and it will kind of disappearing for a few weeks in March 2025. Unfortunately, this will happen when Saturn is conjunction with the Sun, so we won't see this event. On December 8th, the moon will occult Saturn, and unfortunately, this event is only visible from Indonesia. Even on Saturn, there are interesting events because this time of the orbit of Saturn, the perspective makes possible to see some of the moons passing in front of Saturn. But the problem is that Saturn is much farther away from the Sun, and the moons are smaller, unless it's Titan. And I found that there are a couple of events on December 6th and December 22nd, although these happen just after sunset, but this is possible to see them, like this one on the 16th is at 5 o'clock. You can see this little shadow, this Titan. And this is 22nd. So let me know if you are able to see that. Uranus in December is also evening object. It's not too far from the Pleiades. And this is image from Stellarium is telling that they are approximately 7 degrees apart. The magnitude is 5.6, while the apparent size is 3.8 arc seconds, and also retrograde until the end of 2024. If you have a small telescope, you can see just a blue-green dot. That's what I can see. But if you take images with a special camera, you can even spot the moons. Can you see them from the image? If not, the next image probably can help you. I can see 4 of the moons of Uranus. Ariel, Umbriel, Titania, Oberon. Miranda is missing here. Sorry. Neptune. This image was taken on September 15 with a monochrome camera. That's why it's black and white. But it's cool because you can see Triton here on the top. And just amazing that you just looking like 4 billion kilometers away, and you can see this small moon. They probably has a liquid ocean in the bottom. I noted this comet, the C2024 G3 Atlas, not because I'm very optimistic, is a grazing comet. That means it can be very bright for a few days, around January 13. But the problem is that very, very close to the sun, and we know what happens sometimes, very often, I would say. The sun grazing comet has just been destroyed when you're closing too close to the sun. But if they survive perihelion, can be a very interesting event to observe. Some deep sky suggestion for December. I just noted three, like the Rosette Nebula in Monoceros, the Unicorn, the Pleiades, of course, and the Orion Nebula. You can also plan your observation with this free online planning tool that is telescopius.com. So that's the Rosette Nebula. This image was taken on February 2024. Sorry, too fast. And this is its location. See, Orion is, if you make a line, there's a line between these two stars, Betelgeuse, and you can find like all the distance, and this is where the Rosette Nebula is located. It's a giant molecular cloud. So if you have a narrowband filter with your equipment, you can have beautiful images like this one. The Pleiades. Not much to say. The Seven Sisters. This is one of the most famous open cluster with lots of blue gases. They're here, and if you have a light pollution filter, even from a light polluted area, you can take beautiful images like this one. I will try again as soon as possible. And nothing to say about the Orion Nebula. This is just 15 minutes of total integration time. Unfortunately, it was clouded, and I didn't have any chance to take other images for last year. Let's see if I can try again. And it's so beautiful. You also see the running man here, M43. A note about the meteor showers for this month. We have the Perseid in the Ursa Major, and they're active between December 17 and 26. It's caused by the comet 8P periodic Tuttle, and its orbit around the sun every 13 years. The best time to view this shower is at pre-dawn hours where the radiant is higher in the sky. Then there are the quadrantids. They're a very narrow peak. In this case, lasting only about 6 hours. The best night for this meteor shower is January 2nd to 3rd. Probably is around 7 p.m. Universal Time, so is during the day here. Interesting because this meteor shower is generated by not by a comet but by an asteroid. And interesting enough, when it's high enough in the sky, it can generate over 100 meters per hour, but just for a very few hours, as I said before. And finally, this is one of the best meteor showers of the year, the Geminids. And unfortunately, we have almost full moon that will compete with the light. But the good thing is that most of the Geminids are very, very bright. And again, these are generated by an asteroid instead of a comet, the asteroid 3200 Phaeton. You can even catch 120 Gemini meteors per hour during the peak. From mid-evening, the best time of the day is around 2 a.m. Then we have visible passes of the International Space Station. This is a website, heavens-above.com. And you can see there are a few at the beginning of December, not particularly bright. The brightness is minus. This was yesterday. Minus 3.6 is very good. -1 is good enough. But if you scroll the next few days, you can see on December 16, minus 3.8. That's a very bright one. It's happening early in the morning, I would say. And again, the next few days, you can see minus 3.8, December the 30th. In January, again, we have minus 2.3. So the brightness with a minus sign and the higher number, it means usually that is almost overhead. This is happening on December 29, is the brightest one, between 7:12 and 7:20 a.m., when the maximum altitude will be 64 degrees and the distance will be only 462 kilometers. You may run this simulation for your location very often because this is changing quite a bit because there are continuous correction of orbit, and this can definitely be a different time. Even more for the International Space Station at Young Lunar and Solar Transit. There is this website, transit-finder.com, when you can also see if there is any pass of this brighter object on the front of the moon and the sun. Of course, if it's going where the sun, never look directly at the sun. And as I mentioned, the transit properties may significantly change depending on observer's location, especially long travel distances. So recalculate 1 or 2 days before the pass. Space exploration, there are a bunch of Starlinks, not much to say. And there is a launch site on December 4th, so it should be today. It already had happened from India. The Indian Space Research Organization, the Proba 3 spacecraft, on behalf of the European Space Agency. And then we have a Vega launch and a Falcon 9 with other Sirius XM, other satellites. And with that, I think I'm done. Thank you so much for your attention. If you have any question, just ask. Thank you, Tom.
And thank you very much, Claudio, for a wonderful presentation. Do we have any questions?
Yes, we do. From Zapfan, he asks, can you see the Chinese space station from there? I'm too far north, and he's asking if we can see it from Toronto. Zapfan asks, can you see the Chinese space station there? I'm too far north, and he's asking in relation to whether we can see the Chinese space station from Toronto.
Claudio, can you hear me?
I can hear you, Tom. I can't hear the question. If
Okay,
Ennio asks, yeah, if you can repeat, I can just
sure.
answer if you can.
The question is, can you see the Chinese space station? I'm from Toronto.
Yes, you can. Yes, you can. As I showed you before, this is a puzzle. It is much smaller because also the distance you can see is much far away. If you remember the slide before, so the International Space Station was only 462 kilometers, the closest, while the closest passage of the Chinese space station is 1,000 kilometers. So it's much smaller, and also the diameter, of course, is much smaller. So the answer is yes, but you have to know where to watch, and yeah.
Okay, thank you. Any more questions?
We have no more questions.
All right, that's it for questions. Okay, Claudio, thank you very much. And we will go quickly to fun facts while we switch over for our next speaker.
Yes, microphone is on.
Oh, okay.
Oh, hi.
All right, so we were faster than I thought. Ladies and gentlemen, Arushi Nath, take it away.
Thank you very much. It's great to be presenting here at the RAS Toronto Center once again. My name is Arushi, and I'm a grade 10 student. And today I'll be talking about using n-body simulations to analyze transit timing variations in exoplanetary systems with multiple planets. So let's get started. So first, what is an exoplanet? Exoplanets are simply planets who orbit stars outside of our solar system. So let's look at a simple GIF of an exoplanet right now. Here, you can see the exoplanet is orbiting around its host star because of their mutual gravitation. You will notice that as the planet goes in front of the star, a small portion of the star's light is blocked, creating a dip in its light curve. And the planet will go and transit once again, and the dip will be observed once again. An interesting thing is in a single planet system, the planet's orbital period is constant, which means after a set amount of time, the dip will happen once again, and we'll be able to predict when this dip would happen. But let's say we make it a bit more complicated. What happens if there's multiple planets in the system? Let me play this GIF here. So now you can see there's multiple planets. And now there's not only the gravitational interaction between the star and the planet, but also in between the planets itself. And this creates shifts in the orbital period. Let's look at these figures. Let's look at the inner planet, which is orbiting. It's getting pulled towards the outer planet, meaning that the known planet will be sped up a bit. And this means that the transit will occur earlier. The opposite can happen too. Let's look at the figure below. Here, you can see the inner planet is orbiting and the outer planet is behind it. Because of their mutual gravitation, the inner planet will be pulled towards the outer planet, and this will make this planet slow down a bit, causing the transit to happen later than expected, which means that transit shifts can be observed between transits, meaning that the planet's orbital period is not constant. So what would happen if we plotted this orbital period each time? Look at this curve right here. Here, I've plotted the light curve of the transit for 9 different orbital periods of the planet. You can see that there are slight variations. In the start, it happens right at the center. You can see that here's the mid-transit. But in the second epoch, you can see that the mid-transit shifted a bit towards the right. And for reference, the blue line, vertical line right here, is the predicted mid-transit time of the exoplanet. So what can we find out from these curves? Well, let's say first epoch 1 is normal. We can see that the mid-transit time happens exactly where predicted. Now let's look at the second orbit. Here, the second orbit happens a bit later than predicted. Same for the third and fourth. And then suddenly it's happening earlier because of the mutual gravitational pull between other planets. So what happens if we subtract the observed mid-transit time and the calculated mid-transit time? Then we can create what's called O minus C plots, or observed minus calculated plots. So here you can see epoch 1, observed and calculated were the same, so it's 0. Epoch 2 happened later, which means the observed minus calculated is positive. And I've done the same for all of the 9 orbits, and you can see it produces a curve. So now let's look at an O minus C plot of an actual known exoplanet, Kepler 9. And here we can see the O minus C plot of 2 of its planets, Kepler 9b and Kepler 9c. You can see there's a trend you can see, which is very periodic. The orbital period of Kepler 9b varies by about 45 minutes during these observations, and the orbital period of Kepler 9c varies by a lot more, by about 140 minutes. What happens if we combine these two curves together? Here, one thing you will notice straight away is that both Kepler 9b and Kepler 9p display really out of phase behavior. This means that they're basically doing the opposite. While one is going up, the other curve is going down. And this is actually what we should be expecting. And the reason for this is because the mutual gravitation between the two planets, as they're pulling towards each other, one will slow down and one will speed up, meaning that one will orbit earlier than expected, one will orbit later than expected. You'll also notice if you look at the y-axis, it's a big transit time. The observed minus calculated has a very big difference. It goes from about 25 to minus 25 for planet B, and it goes from like 60 to minus 80 for planet C. And this strong signal is because of their near resonance orbits, which means for every 2 orbits the planet B makes, the planet C completes 1 orbit. And this really demonstrates how looking at the observed minus calculated plots, also called transit timing variations, can confirm the presence of multiple planets. Actually, Kepler 9b and C were the first exoplanets for which TTVs were detected in 2010. So, what is the significance of measuring transit timing variations? Well, there's three main points. First, using this, you can validate the presence of known exoplanets, as we saw right before with Kepler 9b and C. Simply by looking at their transit timing variation plots, you will definitely notice that there has to be another planet. Second, it can also reveal the presence of additional exoplanet. If you only saw one of those TTV curves, you would note that there is likelihood another planet in the system, which can reveal a multiplanetary system. Third, as you might have remembered before, I said that these TTVs are caused because of the gravitational pull between planets, which means that by observing these transit timing variation curves, and by looking at their shape, by their amplitude, we'll be able to determine planetary masses and orbital characteristics of both planets. And this technique is really powerful because it can reveal properties of exoplanets that don't even transit the star. So far, we have been able to detect 32 new exoplanets through transit timing variations. But there's a few challenges with transit timing variation analysis. First, there's a lot of noise. And because when we're looking at these TTV curves, this is all based on the mid-transit timing of the observation. This means that when observing the mid-transit time, we need really precise observations. But there's always instrument noise, sometimes there's multiple stars, sometimes there's calibration errors, and all of these errors can add up, and we have to make sure we don't confuse these errors with the TTV signal. Second is obviously observational constraints. Because limited transit events for long period planets are possible, because they only orbit, let's say, every 100 days, 200 days, which means we might not have enough observations. In addition, sometimes telescopes can only take observations every 10 minutes, 30 minutes, and let's say the period of the exoplanet is really small. That means that there could be some gaps in the data, and this can produce a few errors in the measurement of the mid-transit time. Third, and a very important point, is degeneracy. Because these TTV signals are based on the orbital parameters of the planet, it's important to note that similar TTV signals can be produced from different planetary configurations, as we'll see a bit later, and this can really complicate the interpretation of mid-transit timing variations. Finally, there's multiple effects that can cause variations in the transit time, including orbital decay and light time travel time, and we have to make sure we do not confuse these with transit timing variations. Luckily, TTVs, because of multiplanetary systems, have very short periods compared to orbital decay, meaning that we can distinguish between them. But it's also very important that we learn to subtract the orbital decay from the curve. So let's look at degeneracy. Here you can see the plot of two different planet systems. In the first one, you can see the mass is more and the centricity is less, 0. In the second plot, you can see the mass is much less, but the eccentricity is more. But you'll notice that these produce near identical transit timing variation plots. This means basically mass and eccentricity produce very similar signals in TTV plots, making it difficult to determine which one is causing the signal. Or maybe it's a combination. There's also other degeneracies, for example, with mass and orbital distance, and eccentricity and inclination. So my project had three main goals. First, generate thousands of n-body simulations that accurately model these gravitational interactions between planets in multiplanetary systems. Second, train machine learning models on these synthetic data from the n-body simulations and validate their performance using data of real exoplanets to identify these TDV signals caused by the planets and find their properties. Third, use the machine learning model and other techniques to break the degeneracies in parameters to be able to accurately determine all of the orbital parameters of the exoplanetary system. So here is a quick look at my methodology. So first, I'm creating n-body simulations, which is really important. And this is done by varying the orbital parameters. Second, I'm using real data from the 32 known TDVs to be able to determine the parameters for the n-body simulations. Third, I'm creating thousands of n-body simulations to be able to train my machine learning model on. And fourth and fifth is still ongoing, but creating a testing set for machine learning model and identifying significant transit timing variation for further analysis. So first, generating the synthetic TdV curves. So here I use 7 parameters. I use the mass of the planet as well as the 6 orbital parameters. So the mass, the orbital period or semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perastron, and mean anomaly. And all of these have different roles in the creation of the TdV curve. So here is the algorithm that I used to generate n-body simulations. So it's based on both nbody.ai and Rebound. And you can see a sample of my code here. And using this code, I'm able to generate an n-body simulation, as you can see here, which is basically an O-C curve. Second, parameter optimization. And this is really important because we want our bounds when creating n-body simulations to be realistic and match with real data. So to do this, I set up constraints based on the current 32 TDP detections taken from the NASA Exoplanet archive. And based on this, I was able to create ranges for the planetary mass, orbital period, eccentricity, inclination, and argument of perastron, which I fed into my n-body simulations to make the data realistic. And these n-body simulations were run on 2 planet systems. So there's the known planet, the perturbed planet, which is experiencing the transit timing variations, and there's the perturbing planet, which is causing the transit timing variations. So third, now that I had my n-body simulations running and I had all my parameters and constraints set up, now was the time to create the training set for machine learning models. So far, I've generated over 12,000 n-body simulations generated on my non-GPU computer, and these are basically to mimic realistic scenarios. In addition, 10% noise has been added to account for instrument errors, uncertainties, and a few unaccounted effects. Validation. So I was able to validate my n-body simulations to match with real data on Kepler 9b. You can see that both the O-C curve for planet B and planet C match very well with the literature. Thank you so much. In the future, I'll be making my machine learning models and I'll be creating my testing data sets using the real data. So thank you very much. I'd be happy to answer any questions.
Thank you very much, Arushi. That was a wonderful presentation. Let me just see here. Okay, so we have some questions. With your Python code, have you had a chance to run without the global interpreter lock and see if there's any discrepancy with your result?
Actually, no. I'm actually not too certain what the. Sorry, could you repeat that question? The first part.
Okay, so the question is, with your Python code,
Yes.
have you had a chance to run without the global interpreter lock and see if there's any discrepancy with your result?
No, I haven't experimented with the global interpreter lock at all. I'll have to read up on that, and maybe if it's something that would improve my TTV simulations, I'll definitely try that out. But thanks for pointing it.
Okay, and then the next question. Okay, so the next comment is unistellar telescopes are used to follow up exoplanets by amateurs. 3.5-inch mirror, I believe, from Zapfan.
Yes, that's true.
And then Louis R would like to know what software are you using for your LLM?
So I'm actually not using any LLMs in my project. So far I've been creating the n-body simulations, which do not use any machine learning. In the future, I will be using neural networks to be able to use the training data of my n-body simulations and be able to predict the parameters.
Okay. And then from Pavel, is it difficult to distinguish TTV due to other planets from, for example, apsidal precession due to the star's flattening?
That's a great question. And actually, yes, because transit timing variations caused by gravitational interactions is really unique in the way that the period that this happens is really small. So it happens every few transits. You can see there's a huge difference in transit timing variation caused by the gravitational pull. And also, you will notice that TTVs are almost like sinusoidal curves. So they keep repeating each other over and over, which makes it easier to distinguish between that and other effects. But it is also really important, even if we know how to distinguish between this and, let's say, the uh, apsidal precision, it's really important to still be able to remove the effects of apsidal precision and other effects so that we can totally isolate the TTV signal due to other planets.
All right. And, oh, hold on a second. Some more questions coming in. Are people looking for moons around exoplanets using TTV?
That's a great question. And in fact, it's definitely possible to be able to look for moons. And those moons would cause a transit timing variation too, just like planets. And I believe people have tried. I'm not sure how successful they were, but it's definitely something that has been experimented on before.
Okay. How powerful a telescope is needed to detect exoplanets?
That's a great question. And honestly, it doesn't need to be very, very big or very huge telescope. And even small telescopes by amateur astronomers can be very helpful. Actually, there's several initiatives. For example, Exoclock, which is actually meant to basically build a network of amateur astronomers with small telescopes ranging from 6 inches to maybe 12 inches and 14 inches in diameter. And these are used for follow-up of exoplanet observations. And so as long as you have a telescope, you'll definitely be able to observe most exoplanets, especially since exoplanets are simply discovered by dips in measurements of a star's light. And most stars are really bright and we can observe them easily. To be able to detect an exoplanet, however, is slightly harder simply because most of the exoplanets that we have the capabilities to detect have already been detected. But even if you can detect an exoplanet with your own telescope, you can definitely help in improving the ephemerides of known exoplanets or contributing to observations of exoplanets where maybe not enough have been done. And I think that's a really important role of amateur astronomers right now.
Okay. And next question. Referring to your previous presentations, how did you get into studying exoplanets and asteroids?
Yeah, that's a great question. And honestly, I think RASC has a big part to do in it. That's where my interest and love for astronomy started. And I remember I used to be really fascinated with planets before, and then I remember looking through a huge telescope and then seeing other objects that moved, like asteroids, and it made me fascinated. And I wondered, since so many asteroids, for example, I started with asteroids, so since so many asteroids are out there and we haven't detected all of them, I became really curious on how to detect more asteroids. And then from there, I learned to basically create light curves of asteroids. And I think in the past few years, especially, I've been really interested in performing precise photometry, which is basically looking at minute change in light coming from celestial objects. So I started from asteroids, and then I think the natural path for me was exoplanets. And exoplanets, it's almost applying a similar technique because exoplanets, I'm also looking for precise changes in brightness during the transit. And so that's what I'm working on right now.
Okay. And our last question. What is the furthest exoplanet discovered to date, and what's the closest?
That's a great question. And actually, I'm not sure that's something you'll have to research on your own. I don't have the stats with me, but definitely there'll be some information. And um, over almost 6,000 exoplanets have been discovered so far. So definitely do some research, and I'm sure you'll be able to find the closest and furthest.
All right. Well, thank you very much, Arushi. That was wonderful.
Thank you
Okay.
so much for having me.
Now, just give this one moment here. Just a moment here, folks. Just got to load up the announcements. Okay, so that concludes our presentations for this evening. And so we're just going to go into some brief announcements, and then we are going to go on to our annual meeting. So let's get to the announcements. So for those of you who are joining us live, welcome. This is one of two types of meetings that we have here at on with the Royal Astronomical Society of Canada, Toronto Centre. You've just seen one of our recreational astronomy nights, and then we normally have a speaker come in from the professional community to talk to us, but not in December because of the holiday season. So, for those of you who are joining us live, please say hello in the YouTube chat. Please enter some questions for presenters. If you're a new member, please introduce yourself. And you're coming to us from far outside the Toronto area, please let us know where you're coming from. So, like I said, no speakers night in December. We'll see you in the new year for our next speaker. And then coming up, our next recreational astronomy night is the 1st of January, 7:30 p.m. online only. Andy Beaton will be talking about the sky this month, and Frank Dempsey will be talking about Frank's current visual observing projects. We've also got one more presentation slot available. So yeah, drop us a note at president@raskto.ca, and if you'd like to present something. So like I said, this will be online only. Coming up the DDO in the next couple of weeks. So Gigantic Jupiter, the gas giant at opposition, will be at the DDO on Saturday, December the 7th from 9:30 to 11:30 p.m. Registration fees are as shown here, and you can register online with the links at raskto.ca. And then coming up on Friday, December the 13th, 7:30 to 9:30 p.m. At the DDO Astronomy Family Night. The topic is Mariner 2's close encounter with the planet Venus. So again, registration fees are as shown here, and again, the links can be found at raskto.ca. The Carr Astronomical Observatory is open. Operations are largely back to pre-pandemic conditions. The only thing that we ask is that we encourage, that masking is in common areas, but the preference of the people in attendance will be taken. Please see the CAO bookings page for all details at the link shown here. Reminder that the Toronto Centre runs on clean renewable energy. We're always looking for additional help. If you're a RASC Toronto Centre member and you're interested in helping out, if you got some free time, please drop us a line. Volunteer at raskto.ca. So, RASC Toronto Centre has paired up with Benevity to receive charitable donations. If you are a volunteer and your employer has signed up to make contributions for charitable work, let us know at either president@raskto.ca or treasurer@raskto.ca. Reminder that to sign up or to renew your membership, if you like what you see and you'd like to become a part of the RASC Toronto Centre, you can do so at secure.rask.ca. Gift memberships for the holiday season are also available at National Office. Contact the National Office at mempub@rask.ca. Now, we've run a little late, so the 2024 annual meeting will begin about 10 minutes after we sign off for the evening instead of at 8:30. And please use the Zoom link that you were emailed after you registered. And for those of you who will not be joining us, RASC Toronto Centre would like to wish you a very merry solstice and a happy perihelion. So, have a pleasant evening. Thank you very much for joining us. Please follow us on all the social media that we've got listed here. If you've been watching live and you like what you see, please like, subscribe, hit the notification bell, and do all that other good YouTube stuff. Be safe and keep looking up. Good night, everybody.